I am so excited to see people here from across the world. I see people as far west as the west coast of the United States, as far east as Belgium. Please speak up if you're further east than that. This is obviously all from a very East Coast centric standpoint because depending on where you are, might be further east or west. But it's been so great to have so many people here coming to these talks from around the world. And we're so excited to have you all here. So without much further ado, I'm going to introduce Tom Falcon Berry, who is an associate professor at Tarleton State University in Texas, which, as he mentioned, is right up the road from Dublin, Texas. His research fits at the perfect intersection of numerical cognition and statistical modeling and inference to fit all of our interests here as a part of the Mathematical Cognition and Learning Society. He was supposed to be giving a related talk to this one in Dublin in 2 weeks, but what's better than being in Dublin than being in our own homes or offices and talking about this from afar, possibly in our pajamas. So I'm going to turn it over to Tom. I've asked him to give a very kind of intro to Bayesian modeling, Bayesian inference, kind of why and how to use Bayesian rather than frequentist statistics. For full transparency, this was almost entirely selfish because I love statistical modeling and know very little about Bayesian modeling. So I asked him to teach at the level where I'm prepared to learn. So if you have been to one of Tom's talks before, this might be a repeat, but hopefully everyone will learn something. I'm sure Tom could give this talk in his sleep at this point, but we are going to turn it over to him. Thank you so much for being here.
All right, thanks so much, Andy. I am so pleased to be here. And if anyone attended my talk at Ulster, listen, I said at Ulster, I was actually sitting in the same chair right now, but if anyone attended that talk last week, there will be some overlap here, but I also have to overlap one of the jokes that I told, which was, it is so good to see so many people that I usually have to have a passport in my back pocket to see. So it is kind of nice to have right now 63 participants all hanging out here to talk about Bayesian inference. Now, this is a bit of a challenge today. What Andy has asked me to do is something that I would usually want a 2 to 3 hour workshop for. And what we're going to do is try to condense the really essential parts of Bayes, particularly the why and the beginnings of how, condense that into about 30 to 40 minutes, and then leave you the rest of the hour for some questions. So yes, some of you will see things that you've heard me say before, but you'll probably hear me say it in a different way because I never give the same talk twice, even if the slides are the same. But I've gone to giving talks where I handwrite a lot of stuff, so that really guarantees that something new will happen each time, and I hope that's a good thing for us. So I'm going to share my screen and get started. I think the way this will work is if it were a workshop, I would just take questions along the way, but I don't want to take too many questions that lead us astray without getting through the primary material. So if you have a clarification question about something that I have said, please, by all means, ask, put it in the chat. I think Andy will be monitoring the chat for us. If you have a question about, well, what if, or how would I do this, wait until the end, because I'm going to try my absolute best to make sure that we have time to address some of those questions at the end. So let's go ahead and share the screen, and hopefully you all can see somewhat of a title slide now. So we're going to talk about Bayesian methods in mathematical cognition. I could really just erase the in mathematical cognition part, because this is really just the basics of Bayesian inference, period. It doesn't matter what the content area, but the example that I use to guide us will certainly be from math cognition. And I want to mention this is a conceptual overview. So we will talk about how to compute some Bayesian stuff, but it will be at the level of using some good software for that, namely Jasper. If you've never seen that before, you'll see that today. I do want to say that the slides for this talk will be available at my website, which you can see written there just underneath my affiliation. And if you don't follow me on Twitter, I want to give you a reason to do so. It's a very selfish reason. Let me go here to Twitter. You can see right now, let me refresh this. You never know what happens in real time. Right now, I have 982 followers. I want to hit 1,000 today. So I know there are some of you out there that are not following me right now. If you want to see more Bayesian goodness and stuff related to math cognition, then certainly let's take a look at Twitter. And then the last thing that I'll say is a lot of what I'm talking about today is coming directly from a new paper that is going to be appearing in the Journal of Numerical Cognition soon. And that is this paper here, Bayesian Inference and Numerical Cognition, a tutorial using Jasper, co-written with Alexander Lai and E.J. Wagenmakers. And the preprint is here, and I'll also write the web address of the preprint on my talk here in just a couple of minutes. So let's get started today, and let's give a quick outline of what you can expect in our hour today. The first thing is that you are certainly going to get a conceptual background, some conceptual background for Bayesian inference, just kind of what it is and how it works. We will talk about an issue that some of you always want to talk about, and it's an important issue, and that's the distinction between what we mean by priors on models versus priors on parameters. In my experience as a teacher of Bayesian inference, I think this is the one thing that is the most confusing at first. And I don't care how many times you have thought about it or seen talks about it or even used it yourself, it's always a good idea to step back and separate these two in one's head. And then finally, we'll give a nice detailed example using Jasper with a reporting template. So you'll leave here today with some idea of how to write up the results of a very good basic Bayesian analysis. And as I mentioned before, this comes directly, or a lot of this, the motivation here comes directly from this new paper that will be in the Journal of Numerical Cognition soon. And I will say that these slides can be downloaded from my website here. And I'll give you another link to this at the end of the talk. So let's get started with an example. So let's suppose that we are interested in assessing the effectiveness of some mathematics instruction program. Okay, so there you go. That is what makes this for the math cognition community. It's not a very deep math cognition example, but it's certainly one we can get our heads around. So we're interested in assessing the effectiveness of this thing. So we've implemented this program, whatever it is, and then importantly, we measure mathematical ability using this wonderful scale for advancing mathematical ability. We're going to call that the SAMA. And it is a national assessment. And it turns out that this national assessment has a known mean score of 50. Now, we give this to our people who have taken this instructional program. We had a sample, and that sample had a mean of 54.4 and a standard deviation of 10. And so our question, as we would ask for any beginning statistics student, is did the training work? And we are going to answer that question today, but we're going to do it in a way that goes a little bit beyond what we would do in a typical first-year stats course. We're going to look at this from the point of view of how a Bayesian would address this problem, and then we'll go into Jasper to actually do our computations. So I want to begin, just again with some background, what we consider as a basic statistical framework. Now, this doesn't matter whether you're a frequentist and you use p-values, or you're a Bayesian and you use the things associated with Bayesian inference. We're still going to do these basic two things. We are going to define a couple of competing models. We sometimes call these hypotheses. And these are models that could possibly generate the data that we observe. Usually the way we do this, and certainly the way we'll do it here, is we'll make one model where the training worked. Okay, actually there was an effect of this training. And then we'll make a model where the training didn't work. Sometimes we'll call that the null hypothesis. So we set up these two competing models. Now, for more complicated situations, you might have more models than just these two, but for today, we're going to limit ourselves to two models. Once you have these two models or hypotheses defined, then we want to assess the fit of these models against the data that we've observed. Models are just models. We need to see how well they explain the data that we're seeing. So that's a statistical framework that I'm sure we're all mostly familiar with. The big question that you have today likely is, how do we proceed? So let's get a little bit into some of the technicalities of how we proceed. Well, first, we needed to define these competing models. So we're going to do that. We're going to define a couple of hypotheses about the population level effect size. And that little symbol, if you're not familiar with that, is a Greek letter delta. So you can think of that as just being the population level of, say, Cohen's d or something, some sort of effect size that we're familiar with. So we want to define a couple of hypotheses about this delta. We'll define one hypothesis where delta is, we'll define one hypothesis where delta is 0. So you'll notice that would be the case if the training did not work. There would be a 0 effect. We'll call that the null hypothesis, denoted H0. And we'll define another hypothesis, we'll call it H1, sometimes called the alternative, where delta is not 0. Now, of course, you might have some more expert knowledge about this training. You might actually predict a model where delta is bigger than 0. And it's certainly easy to specify such a thing in your software, and we'll do that a little bit later. But for ease right now, we're just going to consider the two-sided effect of it just being not 0, maybe positive, maybe negative, who knows. And so what do we do with this? Well, what we're going to do now is probably very familiar to everyone. We collect data. And that's why we're in this game. We're going to collect data, and we collect data because we want to see how well these hypotheses hold up in light of that data. So let's collect the data. Once we've done that, what happens? Well, I'm going to take you down one of two paths once we collect this data. The first path is the frequentist path. This is the path where we compute this probability, and this probability that you're seeing is the probability of getting our data, or more extreme, if the null hypothesis is true. Now, the symbol there is the probability of the data given H0, or conditional upon H0. Now, this is familiar to everyone as a p-value. When we compute those p-values, this is the probability that we are getting. We're saying this is how likely these data would be to occur if the null is the true model. And of course, the way that we then interpret that p-value is as follows. We say, well, if p is small, so sometimes we set a cutoff, sometimes we argue about the cutoff, but let's just say if p is small, these data are rare under the null. That means they're very unlikely to occur if the null is true. And then we argue, well, we have these data, so it must be the case that H0 is just really not a good fit. It's just not a good model of these data. And so our action is that we reject the null in favor of the alternative. So that's pretty familiar to most people. That's the frequentist path. So what would be another way to do this? Well, another way to do this would be, instead of computing the p-value as we would on the left, we can compute something else which we denote BF01. And those of you who've seen this before know that that is a symbol for the Bayes factor. The Bayes factor is this fraction right here. You can think of it conceptually. Now, this is not entirely true, but when you're beginning to learn things, it's okay to make lies about stuff. And this is one of those little statistical lies that you could start with. You can think about this as a combination of a couple of p-values. Okay, that is, again, not at all what a Bayes factor is, but if you want to help think about how the Bayes factor is different from the frequentist way of doing things, think of it as you also add a p-value for H1. Okay, p-values assess the fit of H0 and they ignore H1. The Bayes factor puts them both into play. And so the Bayes factor is a fraction or a ratio where you consider the what's called marginal likelihoods of the data under both hypotheses. And the way it's interpreted is really quite nice. If that Bayes factor is bigger than 1, then that means that this numerator has to be larger than this denominator. Right? And if that's the case, that means that just simply by definition, my data are more likely under H0 than they are under H1. Okay? That's the only thing that means. Now, on the other hand, if the Bayes factor is less than 1, it means the opposite, because that tells you that your denominator is the bigger one, and so your data are more likely under H1, the alternative, than they are under the null. So this is kind of nice. Let's recap some of the things that we have just said about these two paths. So let's compare and contrast the p-value with the Bayes factor. Now the p-value, as we mentioned, only considers the fit of the null as a potential model for the data. That's the only thing that goes into its definition. And thus, it ignores the fit of H1. The common argument against, or one common argument against p-values is, okay, so you get a small p-value, right? Means that your null is not a good fit. That does not automatically imply support for the alternative, though, because the alternative could also be a terrible fit. The p-value gives you no indication of whether that's the case or not. And so what you get here is this, quote, support for the alternative that is never direct support. It's only indirect. It's double negative logic. It's stuff that my students have trouble with all the time. So that's kind of what a p-value gives you. Let's contrast that with a Bayes factor. So the Bayes factor, again, looks kind of like a couple of p-values stacked on each other. Again, intuitively, that's what it looks like. What it does is it considers the relative adequacy of both models as predictors of the data. And this gives us a way then to directly index support for either the null or the alternative. So we're already now beginning to get some Bayesian benefits, as we like to say. We're getting the ability to get direct support, right? We don't have to go back to this indirect support idea. And we also get the ability to get support for either of these models. And of course, we know that's something that the p-value cannot do. If we fail to reject the null, we fail to reject the null. We don't accept the null. And so the Bayes factor, or Bayesian inference in general, gives us a way out of this. Using this definition of a Bayes factor, let's look at how one would interpret a Bayes factor. Because as most of you know, it's really quite easy to go out and compute some Bayes factors. If you've got some good software like Jasper, put some data in, you'll get Bayes factors. What it really comes into play here is, can I interpret it? So let's look at how we would interpret one of these numbers. Suppose you got a Bayes factor like this. You got a Bayes factor with a subscript of 0, 1, which is equal to 8. Okay, so what this tells you is that the observed data are 8 times more likely under the null than the alternative. This little part right here is very, very important. For example, if instead of BF01, if instead of that you had, let's make this blue, if you had BF10 equal to 8, then this would tell you a different story. This would tell you that the data are 8 times more likely under the alternative than they are the null. Okay? And so you have to pay attention to your subscripts when you're looking at Bayes factors. Because Bayes factors can be used to index support for either hypothesis, they are directional. Okay, so that's something to keep in mind here. Another thing, and I don't think I make a big deal of this in the talk, so I'll say something about it here. Another thing to think about with Bayes factors is that they are, if you have one of these Bayes factors, say 1, 0, that is the reciprocal of the Bayes factor in the other direction. So if you have a Bayes factor of 8 for the alternative, that's a Bayes factor of 1/8 for the null, meaning that the data are 1/8 as likely under the null as they are the alternative. So you can get from one to the other, and sometimes that's an important thing to keep in mind. The next question that people typically have is, well, okay, I got a Bayes factor of 8, so what, right? It's not less than 0.05, or it's not less than it's not bigger than some criterion. What do I do with this? So what we often recommend is that people take a look at some sort of standardized or at least recommended scale for what Bayes factors tell you. And probably one of the most popular of these is the one that Jeffries put forth in 1961. And his ranges are as follows. A Bayes factor between 1 and 3 is sometimes considered anecdotal evidence for whichever model gets the support. 3 to 10, considered moderate. 10 to 30, strong. 30 to 100, very strong. Bigger than 100, extreme. I mean, you can just keep going here. I do want to point out, it is extremely important to realize that these are only guidelines. There are no hard and fast rules about when a Bayes factor is, quote, big enough. I think one of the beauty parts about Bayes and using Bayesian inference in general is you are, as an analyst, as a researcher, you are required to make your case with what the data tell you. And so it's much better to say my data are 8 times more likely under the alternative than they are the null, than to say I have moderate support for one of these hypotheses. You can say both of those things, but just saying you have moderate support, it leaves out, well, what do you mean by moderate? Report the Bayes factor for what it is. This is important because let's say you got a Bayes factor of 9.8. Oh my gosh, is that moderate? Is that strong? I would argue, don't worry about the verbal label. Say what you want, but give the Bayes factor and then let the debate ensue from there. People will argue with me on that, and that's okay. And I would say that argument is for another discussion. But I, as well as my co-authors, always recommend that these are only guidelines. So real quickly, I would like to go through kind of the machinery here. How do you get these Bayes factors? How does Bayes work in general? So most of you are likely familiar with the conceptual idea of Bayes' theorem, okay? The idea is that Bayes' theorem lets us use data to update the plausibility of some model or hypothesis. So it probably looks something like this. You get a statement that looks like the probability of some hypothesis given the data is equal to the probability of that hypothesis before seeing data, this is called the prior probability, times some stuff, okay? And I say some stuff because it's really easy to think about this whole equation in this way. You can think about it as the posterior plausibility of your hypothesis. So it's posterior because it's after seeing the data. That posterior is equal to the prior plausibility, so what you thought about the hypothesis before you saw any data, times some updating factor. And that updating factor comes from the relative fit of that data compared to all the other models, right? So given that, okay, this is about one model, you can do the same thing applied to 2 models at the same time. If you do that, if you take the thing that we just saw up here, this little equation, and you apply it to, say, H0 as well as H1, and then just divide them by each other, then you get something like this. And what does all this really mean? Well, this turns probabilities or plausibilities into odds. And so the typical way that I like to think about Bayesian inference, and particularly Bayes factors, is in the following verbal formulation. I think about it in terms of the posterior odds of 2 hypotheses is equal to the prior odds times the Bayes factor. So that Bayes factor now has 2 meanings. First of all, the Bayes factor by definition was the extent to which some observed data is better predicted by one model than another. And that just goes back to our previous definition. But it also has another really nice idea, nice conceptual definition. That is, it is the factor by which my prior odds are updated after seeing the data. And so we'll see an example of how this updating idea works here in just a second. So now I've begun giving you some basic ideas about what is involved in Bayesian inference. And on this page, we started using words like prior plausibility, prior odds. What do we mean by prior? In fact, I'll go so far as to say this is the part that most people, when they first encounter Bayes, think, oh God, this is terrible. We can't be going around if everyone's got a different prior. So I want to address that, that idea, that potential problematic issue by just directly addressing what do we mean by prior when we say prior in Bayesian inference. Well, what we mean is possibly one of 2 things. In everything that we're talking about, there are 2 main types of priors. There are the priors on the models themselves, and then within a model, there are priors on those parameters. So I want to discuss this idea just a little bit further to help disentangle what we mean by prior and hopefully allay some of the concern that you might have about this whole idea of a prior on something. So let's look at priors on models first. So what do we mean by this? With priors on models, here's what we're asking. We're saying before observing the data, what is the relative likelihood of my competing models? Okay, so if I've got a null hypothesis and an alternative hypothesis, in the example that we're dealing with today, there's a hypothesis that the treatment didn't work, and then there's a hypothesis that it had some effect. Right? What is the relative likelihood of those? Is one more likely than another? Are they 50-50? So that is something that anyone can decide for themselves. They can decide this model is 10 times more likely than this one, or as a common default, you can just assume that they are equally likely to each other. In other words, the probability of the null is the same as the probability of the alternative, and they're both equal to 1/2. Colloquially, we call this one-to-one. Hang on one second. There we go. We call this one-to-one prior odds. Now, you might say, well, I do not absolutely believe that you can have one-to-one prior odds. I think any expert is going to come in with some knowledge either in favor of the alternative or in favor of the null. And yes, you are absolutely right. And I'm going to try to convince you that it doesn't matter, that the Bayes factor doesn't care what your prior odds for these two models are. Okay, I'm gonna try to convince you of that. Let's see what happens here. So let's go with this. So you might wonder, if I have these prior odds to begin with, then what happens when I observe the data? Well, when I observe the data, I then convert those prior odds or those prior probabilities into posterior probabilities. And specifically, there's a really nice computation that you can do by hand that tells you the posterior probability of one of these models. I've used H0 here for the example, but it works for H1 as well. That posterior probability is just equal to the Bayes factor divided by the Bayes factor plus 1. Okay, so if you got a Bayes factor of 4, okay, then you would take 4 over 4 plus 1, 4/5, and that's just 80%. That is directly the posterior probability of the null in that case. It's a very simple computation to apply with a hand calculator. I point this out because JASP doesn't actually give this to you for whatever reason. So let's look at an example of all this in play with some hypothetical data and see if we can make sense of the idea that these default model odds really don't matter that much, so that every one of you that's out there today can come into a situation with a conceptually or a conceivably different set of prior odds. Okay. Now, I will say, if you are one of those that doesn't believe that the null and the alternative are equally likely before seeing the data, you can still compute the posterior probability. And if you're interested in doing that, please ask me at the end. I have a formula that I'll show you. So let's do our example. Again, this is a conceptual example. I haven't even opened up JASP yet. We will do that, I promise. Let's say that we are one of those agnostics that says, okay, I don't care. The null and the alternative are equally likely. Any one of these, I have absolutely zero knowledge about this domain. I think these two models are equally likely. So this is before seeing the data. Now, what happens? Well, we collect the data, and we get a Bayes factor for 0, 1, so a Bayes factor in favor of the null of 9. Okay, so what does that tell us? Well, what that tells us is that the observed data are 9 times more likely under the null than the alternative. So our little pie chart here, or pizza plot, as EJ likes to call it, that goes from being half of this little pink color to white, being half and half, it goes to being, well, let's just show you, to 9/10 of that pink color and 1/10 white. Why? Well, because what this Bayes factor is an updating factor on the odds. Let's explain what I mean by that. Before seeing the data, your probabilities are equal. Again, that's the assumption that we've made here. But before seeing the data, our prior odds are 1-to-1, equally likely to be the true model. The Bayes factor is the factor by which these prior odds are updated. So the prior odds in favor of the null will now be multiplied by 9, so that my posterior odds are now 9-to-1. And this is exactly what a picture of 9-to-1 odds would look like. Now that's a little intuitive. If you would like to know how that's actually computed, well, you just go back to the formula that we just showed up here, which is you take the Bayes factor and divide by the Bayes factor plus 1. So in this case, here's what that would look like. It's hidden down here somewhere. It would look something like that. It would be that the posterior probability of the null given my data, well, it's equal to the Bayes factor divided by the Bayes factor plus 1. For this example, that's 9 over 9 plus 1, 9/10. So our posterior probability is 90%, or 0.9 in favor of the null. Okay. So the Bayes factor here is telling me two things. It's telling me the extent to which my data is better predicted by one model than the other, and importantly, it's telling me the factor by which my prior odds have been updated. Now, you may be asking, where are you going to tell me that it doesn't matter what my prior odds are? Well, here's what I'm going to do that. Let's say that instead of 1-to-1 prior odds, maybe you had 4-to-1 prior odds for the null over the alternative. You thought this training program absolutely will not work. I put 4-to-1 odds on it. So what does the Bayes factor do? The Bayes factor scales that up by a factor of 9 so that your posterior odds are now 36-to-1. So you started off in favor of the null by a factor of 4-to-1. You are now even more in favor of the null than you were. You're now 36-to-1. Both analysts here are going to conclude the same thing about this training program. They're going to say that these data have given me evidence that the null is the better model, that there is no effect of this training. Now, this analyst down here, they have a little stronger belief. If you convert this to a posterior probability, well, it's going to be 36 divided by 37, which is much bigger than 90%, but it's still very highly in favor of the null. On the other hand, let's say you really thought this training program was going to work, and you said, I'm going to put 1-to-5 odds here. So in other words, 5-to-1 in favor of the alternative here. So you're going to multiply that Bayes factor. It's going to become now 9-to-5. Right? And so you've gone from a slight sway of prior belief in the alternative to now actually slightly more belief in the null. Your belief, your relative belief in the two models has shifted after seeing data. That's what the Bayes factor gives you, is the extent to which that shift has happened. Okay. So these odds that you come in with do not matter, okay? What matters is in all three cases, the Bayes factor, the extent to which those odds have been shifted, stays the same. This is why in most papers, people report the Bayes factors and not necessarily the posterior probabilities, because the posterior probabilities depend on what these prior probabilities are. And so the Bayes factor is rather agnostic to whatever it is that you choose. Now that's priors on models, okay? The other type of prior which comes in is the priors on the parameters within a given model. And this is a different type of prior. Let me explain what I mean by this. So go back to our model definitions. The null is defined as delta equals 0. The effect size is 0, right? The alternative we defined as delta is not 0. Now, in a frequentist sense, we always, I know when I teach basic statistics with only frequentist components, we just say it's not 0, and then we just go on from there. But one should ask, what exactly do we mean by it's not 0? There is certainly some uncertainty here about what we mean by delta is not 0. Particularly, H1 has infinitely many possible values that delta could be. Now, some are going to be more likely than others. So that uncertainty needs to be coded. That uncertainty needs to be quantified. We, as a Bayesian, can quantify that uncertainty. That's like the thing that makes one a Bayesian, right? If you say, I am a Bayesian, that means on the back of your t-shirt, you really mean I quantify uncertainty. That's all that means. A Bayesian is then going to quantify this uncertainty about that effect size by doing what's called placing a distribution on delta. This is that prior when you start computing Bayes factors that people are talking about. So how do we do this? Well, let's suppose that we're studying something relatively new and we have no idea what to expect. So one objective approach to doing this is to use what we call a default prior. This is one that has been set up by statisticians to have good properties in a wide variety of settings. And so for us, the one that we most typically use in these kinds of problems is we're going to use what Jeffries recommended, and that is what's called a Koshi distribution. And a Koshi distribution is similar to a T distribution with 1 degree of freedom, and it has a particular scale value, or width if you want. And the scale value that we use, again, by default is this one right here. It's technically it's 1 divided by the square root of 2, but in Jasper and other places you'll see it represented as its decimal expansion of 0.707. And not to get too in the weeds about the Koshi distribution, but it works in a wide variety of settings. I want to show you a picture of what this would look like. And this is an important picture because Jasper is also going to give us something similar, and I want to explain in our Jasper example here in just about 5 minutes where that picture is coming from. So here's the thing. Before seeing data, we don't know what effect size to expect, right? We're interested in that. We want to know what is the effect size. If it's 0, then that's support for the null. But if it's not 0, well, is the effect size 1? Is it -1? Is it 0.5? Where is it? This distribution here, this orange Koshi distribution, tells us before seeing data, we think an effect size around 0 is probably most likely, but then it becomes, you know, effect sizes around 0.5 are a little less likely, and effect sizes of 1 are certainly less likely, and way out here are even less likely. So this distribution kind of gives us an indication of our uncertainty about that effect size. And of course, that's prior. That's before seeing the data. After we observe the data, this effect size shifts to a posterior distribution. So now, after seeing this data, we can see that the most likely value is right around 0.5 or so, at least in the picture that I've drawn. And that might not be too surprising, but the posterior is a distribution. So it actually gives us a quantifiable estimate of how likely all the other different values of the effect size are. Now, what you're seeing in the picture from orange to blue is a shift. Again, it's this idea of Bayes being updating or shifting our beliefs. But here's something that's really cool. If you take this posterior and you overlay it on the prior, and this is where a good note-taking software helps with snapping things to the grid, what you'll see is actually quite an interesting picture. What you will see here is, let's consider the effect size of 0, right? This is the one that defines the null hypothesis. Now, before seeing the data, here's your probability that the null is true, right? This is the probability before seeing the data that the null is true, that the delta is 0. After seeing the data, so go to the posterior, here's the probability that the effect size is 0. Here's the probability that the null is true. Notice what has happened. It has gone down. It has decreased. And in fact, if you take the ratio of those two probabilities, the ratio of these is actually equal to the Bayes factor for the null. Okay? That is that's actually quite an amazing fact. And if you get more into Bayesian inference and start doing things for methods that are beyond what Jasper can do, this basic idea still works, and it's called the Savage-Dickey density ratio. And so there's been lots written about this. The reason I mention it here is because one of the plots that Jasper gives us is exactly this idea. And it's a really nice display of how our belief in the null, quantified by this little dot right here, is decreasing by some factor after we observe our data. So without further ado, let's do our example and then wrap up with some time for some questions. So here was our working example. Recall that we tested, let's say, 65 participants, and we observed a sample mean of 54.4 with a standard deviation of 10. Well, the first thing we probably want to do is, just like if we were in a intro stats course is we'd want to compute a t-score for this. So we can do this by hand. We can go in and figure out how far it is away from that hypothesized mean of 50 and then divide by the standard error. We get a t-score of 3.55. Now, in a traditional statistics course, we might compute a p-value for this, go to a table, something like that. But what we're going to do is not that yet. Hang on, sorry. What we're going to do is we are going to use JASP, and particularly we're going to use the JASP Summary Statistics module. Okay, so I've been talking about JASP. Where is JASP? JASP is this thing right here. If you've never seen JASP before, you need to download. In fact, you just like leave the talk now, right? Thanks for coming. Go download JASP because now you're ready to just go play with stuff. Actually, I would recommend you stay around just for a few minutes to see how it works. But it's free, totally free, and does both frequentist and Bayesian statistics. I have it already opened here, so let's go to JASP. Now, JASP usually likes to work on data sets that you've already constructed, but there is one nice little additional module. It's called the Summary Statistics module. You get it by clicking, let me go back out of that real quick. You get it by clicking on this little plus sign and then just activating it. It's already installed, it's just not there by default. So there's the Summary Statistics module. If you have summary statistics that you've computed by hand or that other people have reported in their papers, you can go here and compute Bayes factors for those statistics. Now, this was a Bayesian one sample t-test. You can do it for some other things, as you can see up here. All I need is my t-score, which was 3.55. That is right? I can't remember what I've written down. Oh, yeah, it's sitting right there, 3.55. And a group size of 65. And as soon as I press tab, it starts giving me things. It gives me a whole bunch of stuff over here on the right. Particularly, it gives me a Bayes factor. What I want to do, though, is do a little bit more than just this basic output. I want to also select the prior and posterior plot. So that'll give just a second here. And here you can see several visual elements that we've already kind of come across today. Notice this little pizza plot up here. This is the picture of how likely your data are under the alternative compared to the null. So you can see that we got a Bayes factor of 34.7 in favor of the alternative. Also gives us a median effect size, gives us a 95% credible interval on that effect size. So notice I use the word credible and not confidence because this is an interval that is actually, there is a 95% probability that the effect size is between these two numbers. Okay, so that is a direct probability statement. In fact, you can see it shaded right here as a little interval. And you can also see the shift from prior belief on that effect size. So there's that Koshi distribution to posterior. Notice that it goes, the prior belief that delta is 0 goes from being up here to down here. And the factor by which it does that is that almost 35. Okay. So there's a lot of stuff that you can get here without much input at all. What I would like to do now is I would like to show you how we take this and turn it into something that we can communicate to people. So let me go back to our slides and let's talk about how one would report this stuff. So again, this is just a recommendation, but experience tells me this is probably a good way to go. The first thing that I would always recommend here is to report the results of the hypothesis test. Do the test first. You may be wondering, well, what if I just want to do the estimation? Well, I have something to say about that, so just hang on. First, report the results of the hypothesis test. So what we do here is we define the null, the alternative, and here's the part that makes it Bayesian. We specify the prior under H1. Okay? So let's see what that might look like. And here's something that it might look like. Again, these slides are going to be totally available to you for free to download off my website, and I'll make another mention at the end of where that is, so you don't have to madly copy all this down. So we might say something like, under the null hypothesis, we can expect an effect size of 0. Thus, we define H0 as delta equals 0. Okay? The alternative hypothesis is two-sided, and so we define it as H1 where delta is not 0. And then we specify the uncertainty. We say prior to observing data, we assumed that delta was distributed as a Koshi distribution with this scale. Now, that's the technical aspect of what that Koshi distribution is. I'll show you momentarily how we can change that if we have reason to. Then, once we've done that, only after you've done that, we can report and interpret the Bayes factor. So we have found a Bayes factor of, let's see, was this actually the right Bayes factor? Yes, perfect. Okay. Sometimes it changes on me when I change my example midstream, so I wanted to make sure it was correct. We found a Bayes factor of BF10 equals 34.7. Now, interpret what that means. I would say something like, which means that the observed data are approximately 35 times more likely under H1 than H0. And then I would like to add something about just a kind of a verbal label of that evidence. I can say this result indicates strong evidence in favor of H1. Somewhere in here, you would cite Jeffrey's 1961 as that indicator of what we mean by strong. Okay, so there's your Bayes factor. The other thing that I recommend people do, and I'm saddened that this doesn't happen more, but I got this from Mike Masson a long time ago. I like to do this in all of my papers, and that's to calculate and report the posterior model probabilities for your preferred model. So what do I mean by that? Well, remember earlier, I can take the Bayes factor and I can convert it to a posterior probability for my preferred model. And I do it this way. I say Bayes factor divided by 1 plus the Bayes factor. So for these numbers, that's 34.7 divided by 35.7, which gives me a posterior probability for the alternative of 0.972. And so that might look something like this. Assuming prior odds of 1 to 1 for H1 and H0, our observed data updated these odds to 34.7 to 1 in favor of H1. This is equivalent to a posterior model probability of this 0.97. Okay. Now again, this is where as the analyst, you can change this to whatever you want, but most times I've seen this done, people just assume prior odds of 1 to 1. Oops. Now, once you have done the hypothesis test, then you can report the results of the parameter estimation. Now you might ask, well, why? I've read these books on the new statistics, and Jeff and Bob, they are good friends of mine, but we fundamentally disagree on this notion right here. And that is that to a Bayesian, at least in this framework, estimating the effect size only makes sense if the effect is not 0. If you have support for H0, that's support for a model where delta is 0. There's no estimation that needs to happen then, because you've already done the estimation. You have said H0 gets the most support here. H0 is the model where delta is 0. But if H1 is the preferred model, then that's a whole range of deltas that it could be. So what would be the most likely values? Here is how we can do that. So once we have support for H1, then we need to specify the parameter of interest and remind the reader of the prior. So we might say of interest is the posterior distribution for delta, the population level effect size. Under H1, delta was assigned to Koshi prior with this scale. And then we can report the 95% credible interval, which we, of course, got from Jasper. We'd say the posterior distribution for delta had a median of 0.422 with a central 95% credible interval that ranges from 0.171 to 0.675. Again, these numbers should just come directly from Jasper, assuming that I'm using the exact same example that I started with. Yeah, okay. And that's how that simple example that we started with today could be written up. I do want to point out some more resources for us here, and there's a couple that I can point you to. One is a really good paper by Johnny Van Dorn and a lot of colleagues, and that's the Jasper guidelines for conducting and reporting a Bayesian analysis. And there's the SciArchive address right there. I've got a weird little thing happen with the slash there, but you can just Google Van Dorn Jasper guidelines and you'll get it first hit. And also the tutorial paper that I mentioned that will be appearing in the Journal of Numerical Cognition as well. Okay. Anything else down here? Some closing thoughts. Just very quickly, I want to just give you some pragmatic advantages of Bayesian methods, and then I'll take questions as long as people want to do. First of all, Bayesian methods allow us to assess the degree to which the data make an empirical claim more or less plausible. They are not designed to accept or reject hypotheses. They are designed to update our relative belief in competing models. This works well because we can scale this up to a lot of models and pick the winner, if you will, out of those. Another important idea is we can discriminate between evidence of absence, that is actual direct evidence for a null effect, versus absence of evidence, which is the whole idea of, well, do we really have enough evidence to reject the null or to accept the null? Bayesian methods allow you to do this. I like to think that we can make direct and intuitive statements about the plausibility of models and parameters. The things that we just wrote in those examples were statements to this effect. There's no rejecting and accepting hypotheses. It's just, these data are 35 times more likely under this model, so I believe this model. And here's a range with 95% probability that my effect size would be in. Another really cool thing is you can update evidence as the data accumulates. This gives you the possibility of doing optional stopping and computing Bayes factors along the way, and it doesn't mess with your inference. There's some debate about this, but I really encourage you to read some of those papers, particularly some of the Jeff Rauter work on, I think his papers are always so wonderfully titled. This one is Optional Stopping, No Problem for Bayesians. Take a look at that paper and see if you're convinced. And another thing that I'll mention is that you can incorporate expert knowledge about models and parameters. And so this is through something called an informed prior, which if anybody asks about here in a second, I'll be happy to show you a couple things about that. And so that's all of that. I'm going to go past the shameless plugs for just a minute and give you 3 take-home points. First, Bayes is easy, especially with the right software. Second, Bayes answers the questions you thought you were asking. And third, testing or estimation. Do you have to choose? No, Bayes gives you both at one time. So I will just put this up here, and this ends the formal part of the talk. It always comes in a little bit longer than I had hoped, but we're still within the hour. And I do have some stuff prepared on informed priors if people want to visit about that in just a moment. So yeah, with that, thanks for listening. And I'm ready to hear you talk for a little while. So.
Thank you so much, Tom. That was amazing.
Thanks, Andy.
I'm just literally speechless with thoughts and questions that I have coming out of that. So if people want to identify themselves as having questions in the group chat, you can either kind of write the question out or identify yourself, and then we would love for you to unmute yourself, turn on your video, and ask the question to Tom yourself. Let me give people a couple minutes to write something out. All right, Christoph, do you want to ask your question?
Yes. So, like, recently we can you hear me now?
Yep.
Okay. So, like, recently we had the discussion about like reporting, just simply not to make the table with results too complicated. And then sometimes we had support for null, sometimes we had support for alternative, and there were ideas to either provide like only like to use the values which were positive, so like jumping from 0, 1 to 1, 0, or is it better to stick to 1 and just sometimes use numbers which are like larger than 1 and sometimes the decimals? What would you?
That's a great question, Christoph. So let me re-ask your question just to make sure I'm answering what you're really asking about. So the thing about Bayes, of course, is the symmetry. You can get support for either, and any Bayes factor can be converted into its equivalent form as a fraction less than 1. And so your question is there a recommendation for which one of those to report in a given situation? Is that right?
Yes, and if you have like, let's say like 3 tests, like one of them shows support for alternative, the other for the null, and then like whether it's better to stick to the same BF and then once report the numbers larger than 1 and once the decimals, or how to organize it?
Yeah, so I'll begin that with saying I'm too much of a even though I wasn't born in the 60s, I feel like I'm a child of the 60s, and I'm just like, people can do what they want, right? That's the thing. It's all wonderful here. I think what I would recommend is one of two paths. If you are writing the results in a paragraph and you're describing it in narrative form, I would always report the one that's bigger than one. Report it in terms of the model which gets the most support. I think that to me, that's the easiest one to interpret. But if you have a table where you're trying to summarize Bayes factors for several tests, or you're looking at a linear regression or ANOVA where there's several Bayes factors about the same test that are going on, then usually it's best to put them all in the same direction. And so that would mean that you would end up with some that are less than one. But then, in the bottom of the table, you can explain these that are less than one mean that the other model actually got more support or something like that. But I think in general, it's important to usually, again, with that little asterisk there, it's usually better to report in terms of the one that's bigger than one. Because I think I think they can understand the Bayes factor at first glance much better that way than the fractional one.
Thanks.
Yeah, June, did you want to ask a question?
Hi, thanks for the talk. This is really great.
Hey, you're welcome. Thanks.
So I was wondering, so I think Bayes, from the conceptual point of view, it's wonderful, and the philosophy behind it is really great. But the examples that you showed today was pretty much limited to using basically converting t-values into Bayes factors and then making inferences out of that. So my question here is that I do understand the conceptual advantage of using Bayes, like testing the two different models or more perhaps, but when do the frequentist models and Bayesian models could potentially have different inferences? Mm-hmm. So I thought that was when you have different priors, like you could set different priors for Bayes, and then that's the advantage of it. But then you said the priors actually don't matter in terms of interpreting the Bayes factor. So when do those two two approaches compete each other?
Okay, good. There's several questions. These are great questions, June. Let me see if I can address them pretty succinctly. The first question got around to this notion that sometimes Bayes and frequentist can give you different selections, right? If you think about Bayes as a selection procedure, as in picking the best model, it can give you something that's different from the frequentist. And absolutely that can happen. At the risk of failing miserably, I think I can give you an example with the one sample t-test. Let's do one that's really marginally significant. God, I hate that word, but let's just say 2.01 with a sample size of 200, okay? And so, let's see what happens here. Aha, okay. So notice, the first time it worked. I'm gonna do something a little different here. I'm gonna take away the plot real quick. And I'm going to click to BF01 on the Bayes factor here. Okay, so you'll notice that these results, they give you a p-value of 0.046, which a classical frequentist would say, reject the null, publish and get tenure, or something like that, right? But the Bayes factor is actually 1.76 times more likely, the data are 1.76 times more likely under the null than the alternative. And so if we consider that, the selection, the model selection that comes from Bayes would actually be opposite of what you would get from the frequentist perspective. And there was no tuning of priors required there. But by that, I mean, I didn't have to get off this default for that to happen. So that absolutely can happen, and it will happen often. Usually, often's not the right word, it happens quite a bit in these situations where things are just under the threshold of significance for traditional frequentist things. In fact, that's some of the motivating material that really began to put Bayesian methods into our field about 15 years ago, is when that happens. So the second part of your question, though, was, I thought priors didn't matter, right? So that's a great question, and that illustrates what I wanted to point out about the difference between priors on models and priors on the parameters within the model. So the Bayes factor updates the prior on the models. So like 1-to-1 prior odds for this model compared to this model. It doesn't matter whether your prior odds are 1-to-1 or 5-to-1 or 1-to-5. The Bayes factor tells you how much better the data is under one than the other. But that's for that type of prior. The prior on the effect size, or whatever the parameter of interest is, that absolutely will have an impact on the Bayes factor. And let me illustrate that here. So let me go back to the original 3.55 and group size of 65. So this should give us our Bayes factor of 34.7. Okay, that's what we got with the default prior. Now, you might say, let me plot these. You might say, you know what, I'm an expert, and I've read Gronow, Lai, and Wagenmacher's 2020, and I know about something called this Oosterwijk prior. And so this is a prior where the effect size under the alternative is not centered at 0, but instead is centered around 0.35. And in fact, the prior that I'm going to use is a non-central T distribution. I'm really going to cook this thing. I'm going to put 0.35 as the location, and the scale, give me 1 second, I actually have this on my notes here. The scale is going to be 0.102. I mean, how would you figure that out, right? Well, it turns out you can. And a DF of 3. Okay, there's my prior. Now, what happens to the Bayes factor? Now, the Bayes factor now becomes 203. It's quite a bit different than a Bayes factor of 35. Now, if you're a stickler for labels, this moves from being strong evidence to extreme evidence or really awesome evidence or something like that. I think all the labels are silly, right? This is just, these data are a lot more likely under the alternative than they are the null. In summary, there's a lot to say there. In summary, I think one of the best practices at the beginning is to start with the default prior, because these can be mathematically shown to satisfy most properties that one would actually care about under most situations. So start with the default, so something like a Koshi at 0, that, and then do what's called a robustness check. And so one way to do that in Jasper is just to click Robustness Check, and it will give you Bayes factors for a wide range of Koshi priors. And in fact, it'll show you what the biggest Bayes factor for those kind of priors would be, the one you specified, what if you had some others, and look for the general pattern. There is no prior setting here that makes the null more likely than the alternative. So to me, as the analyst and as the content expert, I'm going to look at this and say, man, regardless of my verbal label, this is pretty strong evidence that there was an effect. Okay, and you just make that, you make your case that way. I hope that helps.
Yeah, thank you. Thank you.
Let's see, Christoph, you had a follow-up if there are no others. I didn't see any others pop up.
Does it because my experience with calculating bias is that basically the things which are like close to significance, especially with large samples, they become at least inconclusive or mild support to null. Yeah. And then was it this big like debate and issue around this paper, or to redefine the alpha level? Wasn't the idea there that if we adapt 0.005 as the alpha, then it would be in most cases convergent with Bayesian?
I don't know if that's one of their main arguments. I'm familiar with the paper, but I really haven't gotten into it quite as much. But my experience tells me when you have p-values that are much, much smaller than that traditional thing, the Bayes factors you're going to get from that are by and large also going to be quite evidential for the alternative. And so pragmatically, I mean, it's pretty good support for lowering your significance level. I actually there was a paper with Sam Shockey that I did a few years back, and I can't remember which one right now, but we did a version of some Bayes factors called the BIC Bayes factors, one of the first sort of Bayesian stuff I started doing. If you go back to that work, we used that to give an analytic argument for why we set our alpha level at 0.01. It was kind of the weirdest hybridization of things that you could imagine, but hey, you know, it was convincing, I think. Now I shudder at the idea that I used that as a formal justification for anything Bayesian, but whatever. Andy, you had a question as well.
Yeah, I have a question. So I think, again, this is fantastic and really thought-provoking. And I think it's great justification, especially for using Bayesian modeling when you have experimental data. From myself personally, I typically do modeling using large-scale prospective longitudinal data. And I know that like M+ has Bayes options and algorithms that you can use. Is that something that JASP can do using structural equation modeling, or anything else, any other approaches for kind of attempting to find causal inference? Or do you think that there's a reason why one might use a traditional frequentist statistic instead of a Bayes factor when doing things using longitudinal prospective data?
That's a great question. So I am not a person to talk to with SEM or any of that sort of stuff. I know the basics of it, at least from the frequentist side. Honestly, I don't know the answer. I know that JASP has an SEM module. I was just trying to load that up, and then I realized you have to have a data set to go in here, so I don't have anything prepared for you. I know my experience from teaching psychometrics is that most of the SEM stuff in JASP is frequentist. But there are Bayesian approaches to structural equation modeling. They're relatively sophisticated. I do not yet know if I don't know if JASP has them yet. My suspicion is that the answer is no, but I know that the folks in Amsterdam that are working with JASP, that is a well-oiled machine of a team, and they are putting new things in this software all the time. In the end, whatever technique you're doing, the things you get out in the end are the same. They're posterior probabilities, they're credible intervals, they're Bayes factors. They're interpreted the same way. And so absolutely, regardless of how complicated one's technique is, I think that there are advantages of this approach to doing them. Sometimes they are a little hard to develop, and you have to really go I like what Jeff Rauter calls roll your own with these things, and that's always fun to do, but sometimes it's very, very frustrating. So it's nice when you have software like JASP that will do it for you.
I'm sensitive to the time. I realize that it's 12:15 Eastern time now. Want to give people an opportunity to ask another question if they have. If not, I know that Tom is incredibly responsive via email, via Twitter. So thank you all so much for being here.
Yes, absolutely. Let me just reiterate, if you don't follow me on Twitter, you know, maybe we're over 1,000 now, I don't know, but we'll see what happens. But certainly on there, I've answered so many and gotten great questions that have brought new ideas to my mind about Bayes just by Twitter mentions and direct messages. And certainly you can email me, and the talk will be available. These slides will be available as a PDF on the website, which you can see right there. And there'll be a little section there on the front page that says talks, and that'll be up a little bit later this afternoon.
Yep. And this is also recorded, and we'll be posting it on the MCLS YouTube channel. That's just awesome. As an update, you have 995 followers right now.
Oh man, 5 more. Come on, folks, you can do it. I should have promised a prize.
Oh, 996. So some people signing off are doing it right now.
I've got a Tarleton State University face mask here. I can mail it to you. How about that?
Thank you so much, Tom.
Thanks, Andy, for inviting me. And thanks to everyone for your questions and for your interest. I always love doing these things. And if you want to talk more about some more complicated stuff, I'm always happy to visit and maybe even do a talk at your university. So just give me a shout.
Great. Thanks, Tom.
Yeah, thanks so much.
Thanks, bye.
997 right now.
Oh, we're getting there. Yeah, Andy, I'm just going to kind of stay on here in case anyone didn't want to be recorded and still wants to ask a question. So
Sure thing. I'm going to end the recording, leave the meeting, and then if anyone wants to stay on, they're more than welcome.
perfect.